let's say you have a function f of x, which equals x squared, and let's say g of x is equal to x plus 1. And let's just say you decide to take in a number like 6, and you're going to input that into f. So if you input that into f, then you get 6 squared, which is 36. And then let's say you decide to take that result and input it into g. You get 36 plus 1, which is 37. So this idea of taking the output of, or taking the input of a function, putting it into that function, and then taking its output and feeding it into another function is what's called function composition. And this is a operation involving functions that's unique to functions. It has no counterpart in the number system. So what we just found here is what's called g of f of 6, and we'll deal with this notation later. But that's what we got. G of f of 6 is 37. Let's try taking 6 and actually first feeding it into g. If you do that, well, g takes numbers and adds 1 to them, so that gives you 7. And then we'll put it into f afterwards. And when you do that, you get 7 squared, which is 49. So here we just found that f of g of 6 is equal to 49. Yeah. Alright, so this diagram here illustrates what function composition essentially does, and we'll look at some notation in the definition in the next slide. But the idea is you take an input, you plug it into your first function g, and then it outputs the value g of x, and then you feed that into f, and that will output a final result. But since you're inputting the result of g into f, the notation you'll see here is this f with a parenthesis g of x in the inside to indicate that we're inputting the result of g of x into f. So let's define function composition on the next slide. So if f and g are two functions and the domain of f contains the range of g, the composition f of g, denoted by f with that little 0, which is f of g, it's not fog, it's f of g, is defined by this rule, which is that f of g of x is written in this way. Now here's a key point that we're going to come across. The domain of f of g consists of all x values in the domain of g, such that g of x is in the domain of f. So that's important because I'm just to draw a visual here. Let's say that the domain of g is represented by this circle here, this blob. This is the domain of g. And let's say we take an input and we feed it into g, right? So when you do that for all the inputs in the domain, you're going to get the range. This is the range of g. Now what we're going to do though, so let's say this is g of x. What we really need to have happen is, if we're going to feed this output now into f, we need to make sure that the range of g is contained inside the domain of f. So I'm going to call this the domain of f. And you see how it contains the range of g? That's important because all these outputs are now going to be fed into f. And then here we're going to get our final answer, which is f of g of x. And this is the range of f of g of x. All right, so all this sentence here is saying is that that the domain of the composition are all the x values in the domain of g, such that g of x is in the domain of f. And here you can see by the picture that g of x is going to be in the domain of g, at least in this visual. So that has to happen, or else your composed function will not be defined. So we're going to compose some functions, and we're going to evaluate those new composed functions for x equals 2 in this case. So let's say f of x equals x squared, And we're asked to find f of g and g of f. So f of g, I'm going to use this notation first, f of g of x, which we write as f of g of x, like that. Well, the way you evaluate this is just to replace g of x with what it is. G of x is defined to be x minus 3, so this is going to be f of x minus 3. And what does f do? F squares things, so it's going to square, in this case, x minus 3. So we're going to get x minus 3 squared. So there's f of g of x. Now let's do g of f of x. G of f of x is to be written as g of f of x. And this time, we're going to input f of x into g. So what is f of x? F of x is x squared. So this is g of x squared. And then g takes things and it takes inputs and subtracts 3. So in this case, it's going to take x squared and minus 3. So there's g of f of x. So notice that you don't get the same result, which means that function composition is not commutative, meaning you can't just do it in either order. You know, addition, multiplication, those are operations on our number systems that are commutative, but function composition is not. So now that we have these, we can easily evaluate f of g, for instance, f of g of 2, which would just be 2 minus 3 squared, or negative 1 squared, which is 1. And similarly, g of f of 2 would just be, using our rule, 2 squared minus 3, which is 4 minus 3, which is 1. All right. The other thing you could do if you wanted to, instead of finding the function first, you could also find f of g of 2 by first finding g of 2. So g of 2 here is just going to be, well, g of 2 is 2 minus 3, which is negative 1. So it's just going to be f of negative 1. And f of negative 1 is just going to be negative 1 squared, which ends up being 1. So we got the same thing we got up here. And similarly, you could do that with g of f of 2. You could actually evaluate, rather than come up with the composed function itself. So f of 2 would be 2 squared, which is 4. So that's g of 4. And then g of 4 would just be 4 minus 3, which is 1. So one thing I want to point out, we got 1 for both of these, but that doesn't mean it's commutative, because we just got lucky. If you plugged in 5, for instance, you're not going to get 5 for both answers. So this was just a coincidence that you got the same answer in both directions.